This is the recording for the pendulum lab. So this is the lab manual, and we're going to go past the motivation and objectives, and then the theory. In the theory, there will be a few that are called a rectangular cuboid, so you need this equation here, volume equals length times width times height. One of them will be a sphere, so you need this equation here for the lead sphere that you will see. And I don't think there is a cylinder or an ellipsoid, so you have to go back to these two equations at some point. Alright, I'm going to go past this one here. On this page here you will find two different methods to determine the immersed or effective mass, and therefore the specific gravity of an irregular shaped specimen. And this is one method here where you hang it on a spring scale, and here is another method where you put the beaker on the scale first, and this is the one we're going to use. So keep in mind that when it comes to that, we're using what is called the immersed mass. So the one on the left here, you will see that in the video. And then when you scroll down, you find this equation here, which is the specific gravity is the typical mass, the actual mass of the specimen divided by its immersed mass. That's all it is. And then you attach units to it, grams per cubic centimeter, in order to get density. The number between density and specific gravity is the same, just one has units and the other one doesn't. Alright, and here's the equipment that I'm using. Yeah, pretty much. I'm not using the tape here, I'm just using the caliper. Alright. So here's an example. It's an old example for brass. I made another example for copper, and I will do that a little bit later. I will go through all these numbers here. This is the first one that I measured for you, iron or steel, and I pretty much already put the data that I measured in here and also the absolute errors, and I will explain them in a little while. And then you have to do the remainder of the calculations, and I will take that copper example and will tutor you through it. So here's aluminum. I know I called it aluminium, but either way. And again, I put the data in here and the absolute errors, and again I will explain that later. Here's the lead sphere. You would have to compute the radius. Well, that simply comes out to 1.78 centimeters. And then here's the water. Notice here mass of empty can is 0 grams. You will see that how I tiered the balance in the video. And then here's the pirate, which is fool's gold. And here are the measurements for the mass. And remember, this is the immersed mass here. The last one here, you don't need this one because you didn't do the effective method mass, or I didn't do it. And then here are the lead also as an immersed mass. And again, I don't need this one here, but this one is the immersed mass. And that's actually it then. Notice that I said skip the conclusion. And then in the addendum, I know this is about the error calculation, but you will see that instead of using this complicated square root, I will just have you add the errors when it comes to that. All right, here are the videos that I taped earlier. So in the next few minutes, you will see the videos. And then I get back to actually doing the example calculation for the copper specimen. This is the copper piece example, and putting on a scale, I measure 290.5 grams. Maybe that can be shown on the camera. And then, as I'm going to measure here, I know it says 10, 20, 30, and so on millimeters. In fact, this 0 here is right. It's between 31 and 32 millimeters. I will call that right away 3.1 centimeters because that's what I need. Then I don't have to convert later. So I'm going to convert right away. So this is 3.1 centimeters, and I'm going to see which one of these lines up the best, and that's the 8 here that lines up the best. So 3.18 centimeters. Then the width here, again 31, which means 3.1 centimeters. And here the best one that lines up is the 7. I don't think that can be actually seen here. The resolution is probably not good enough on the camera. By the way, I don't need to scale at this point. So 3.17 centimeters, and then the height is going to be again between 3.1 and 3.2. So 3.1, and the one that lines up the best is the sixth. So 3.16 centimeters. Of course, this having a hook here means I introduce a systematic error here. So actually the mass that I measured earlier is a little bit too high. In fact, estimating that this is 5 grams, I actually come up with a very good result. Even with it, you will come up with a very good result. All right, and that's the copper cube, the example. So here's the example calculation for the copper cube, and then use that example calculation to figure out the others. I'm going to do the density and the volume first, so I'm going to just look at these numbers and come up with the volume over here, compute the density from it, round the density. After that, I'm going to look at the errors. So here we go. Figure out the volume first, multiply these three numbers here. So here we go. I think I'm typing off screen because not my entire calculator fits on the screen. So there we go, 31.8549696, there it is. At this point, I'm going to take them all along because this is an intermediate result, so I will actually use them to compute the density. So I'm going to divide 290.4 by this number here. I don't have to actually retype it because the TI-84 allows me to divide by the previous answer, hit enter, and I'm going to come up with this one here, and I wrote it all down. Okay, now the thing is, I need to round it. And let's see, there it is. That was actually a little bit off screen here. So I need to round it here. So I have to make a decision, where do I round it? Well, with the significant figures, it gives us a clear understanding of saying, okay, I got 3 sig fig here, not decimals. Significant figures is not the same as decimals, okay? So I have 3 significant figures here, 3, 3, 3. Here I actually have 4. I have to go with the least amount, so 3 significant figures. So this number here rounds to 9.12, 3 significant figures. Okay, on this particular one here, all the rest here, this is irrelevant, except for the 6 here perhaps, because it rounds it down up to 9.12. But the thing is that if you have already an error in one of the first 3 digits, significant figures, then you have completely different numbers way back here. So these are irrelevant and could be considered garbage. Throw them away. You don't need them. You cannot pretend that the result is going to be more accurate than the measurements. If you measure to 3 significant figures, the result can only be 3 significant figures. If you measure 1 significant figure, which by the way is kind of like an estimate, then your result cannot be 5 sig fig. It has to be just 1. So in this case, 3 significant figures, or 4 for the mass, use the smallest one, so it rounds to 9.12. But I want people to write down this ridiculous result from the calculator to point out there is no point of the stuff here in the back. This is micrograms per cubic centimeter or something. It has no meaning whatsoever. All right, so that's the calculation for the density and a long discussion on significant figures. Okay, let's look at the absolute error here. So I found this applet here, and this one here, I prepped this length for this little cylinder here. I'm going to push the caliper on here. Notice that the numbers are always changing, and as I said, I tried to prep it as close as I can. There we go. All right, so this one is squeezed in here. Notice that I'm going to look for where the 0 is actually right here. It's just short of the 3.2. I know it says 3.1 here. What that means is, since the 0 is short of 3.2, I'm measuring actually 3.1 something. And now I'm going to look at which of these little lines, these are fine detailed lines, are lined up the best, and it already tells me that the 8 is lined up. And that gives me the last digit here, so the 3.18. And as I said, that's kind of like the copper cuboid that I measured the length for. So 3.18. Okay, the error of that is half of each of these little marks. Well, half of each one of these is half of 0.01, so 0.005 centimeters, and that's what you will see as the absolute error in the tables. And whoa, oh, I pushed the wrong thing off. All right, so here that's where you see that 0.005. All right, then I'm going to determine what the percentage error is. So I'm going to pull up my calculator again. So the percentage error is being determined as the absolute error, 0.005, divided by the actual measurement, 3.18, and then multiply by 100. Okay. The percentage error should only have one significant figure because the absolute error does as well. So I'm going to round this one here to 0.2%, and then you can see if I divide by the width and the height, which are virtually the same, I'm also going to come up with 0.2. For the mass, I'm going to divide 0.05 grams by the actual measurement of 290.4, and I come up with that, again multiply by 100 to get it into percentage. And again, just one sig fig is needed because the error itself is only one sig fig, so 0.02%. Then in the addendum you find a calculation on how to do the errors properly, but here I'm actually telling you just simply add them. So 0.2 plus 0.2 plus 0.2 plus 0.02 is 0.62, but again the error only takes one significant figure, so 0.6%. Okay, what's the absolute error on the density? Well, here I kind of have to go backwards. So, whoops, okay, I didn't mean to pull that one up. Where's my calculator? There we go. All right, so here I'm going to, instead of dividing as you saw earlier, I'm going to multiply the percentage error times the computed result for the density. So I'm going to do 0.6. Okay, I know that's a little bit off the screen. 0.6 times 9.12. I come up with this number. But, oh, it wasn't 0.06. It was 0.6. I'm sorry. Wondering why did I come up with the same thing, with the wrong thing here. So I'm going to do that. Oh, come on. Can't be this hard. There we go, 0.6. Come up with this one here, but since I was in percentage, I have to divide by 100. So there we go. So I come up with a rounded 0.05 grams per cubic centimeter, and that's the error that you see here. So it is 9.12 plus minus 0.05. That still doesn't quite fit the published density for copper, which is 8.96, but remember there was this hook attached to it on the top, and it just so turns out if I was to subtract exactly 5 grams from the mass here, I don't know the mass of the hook, I'm just guessing 5 grams. If I actually do that, I come out actually with exactly that published density for the specimen. So expect really good results for the others as well. And that's the example calculation. Right, that's the steel. Measures 171.2. And then let's see, the length. Again, it's just beyond 34, so it's 3.4 something, and the third one lines up the best, so 3.43. And this one here, this looks like an inch. In fact, it is. It's just beyond 2.5 centimeters, and the one that lines up the best is 2.52 centimeters. So just short of an inch. That's how they try to cut it, of course. And this one also is 2.5 something, and the one that lines up the best is the fourth here, so 2.54. Alright, this is the aluminium, either way. There we go, and I'm measuring 89.3 3 grams. And the length looks like 2 inches. In fact, it is. It's 5.0 something, and then the one that lines up the best is the 9, so 5.09 centimeters. And again, this looks like an inch. There it is, 2.5, and then 2.54. And then over here, also 2.5, and then the 4 here, so 2.54. Again, I always are looking for where's that 0 that gives me the first 2 digits, so 25 millimeters, which is 2.5 centimeters, and then I'm going to see which one of these lines up the best, and that gives me the third digit, so 2.54 centimeters. All right, the lead ball. $452.1 grams. I'm going to measure this one here. So this is going to be 4.2 centimeters, and the one that lines up the best is the 2. So 4.22 centimeters is the diameter. I should measure in a different diameter since this is a fishing weight, so it's a little bit different in different diameters. Actually, this one reads also 4.22 centimeters. This one, by the way, also has a little hook, so therefore the mass is going to be a little bit off, systematic error. And here it measures 4.22. So this is actually relatively regular. Before I get to the water, just a note on the caliper. So with the caliper, I'm able to read to the closest 0.01 centimeters. And that is why, as I take half of that as my random error, that's why you will keep seeing in the lab manual 0.005 centimeters is the absolute error. For the scale, because here I can read to the 1/10 of a gram, again, half of that would be the error, so 0.05 grams, which you keep seeing. This is the only time, by the way, we're going to use a graduate cylinder. So I'm going to put that on here, and I'm not going to read off the mass. Instead, I'm going to tear it down to 0. There we go. I'm going to fill in the water in just a moment. But here, what I'm going to have is I can read this to the closest 0.2 milliliters, which is also cubic centimeters. So half of that, again, is my error, so 0.1 milliliters or 0.1 cubic centimeters. All right, so with this one here being on the scale, I'm going to fill in the water. And if you listen to the pitch again, you can actually see that, you can hear that it went up a little bit. And I just put too much in there. So let's try it again. And again, I put too much in because I can't read it. I'm going to leave it like this here. Never mind. All right, I'm going to read here the meniscus, and I'm going to come up with 22.8 cubic centimeters, and it says 22.8 grams. So, well, guess what what kind of density you get from that one. All right, that was the water. All right, so for the pyrite, I'm gonna just put this on the scale. And yes, there is some fool's gold in here, but it's actually really not pure pyrite, so it's going to give us a wrong density at the end anyway, specific gravity. So 32.4 grams is the actual mass of the pyrite. Now I'm going to dunk it in water here in a moment. Again, I'm going to tear this one here. And now I'm going to immerse it in the water, and that's why it's also called the immersed mass. And because buoyancy is pushing it up, that's why it will give us a smaller reading than the one we just had. So here we go. Jumps a little bit. Let's call it 9.1 grams is the immersed mass. All right, here's the lead ball again. That should be the mass from earlier, but I don't know, maybe some small error there. We'll see. 452.2 is the actual mass of the lead. Earlier it was, oh, just very, very slightly different. So maybe there's a little bit of water on here already, or maybe the scale is going to be a little bit off. That's why we have an error measurement here. All right, so again, I'm going to tare the water. And of course, buoyancy is going to push it up, but really what it actually measures is how much water the lead ball is displacing. And this one reads, again, it jumps a little bit. Let's call it 40.5 grams is the immersed mass. All right, and that's it.